So welcome everyone. As I mentioned in the post that I put up on the Google Classroom, I decided that I'm going to start the trigonometry unit. Technically we were supposed to start looking at, was a weird thing of the intersection of quadratics with linear relations. But looking ahead I realized that that's actually part of the conics section, and since we're probably going to have time to do that section anyway, I'm just going to leave it till then. So I decided to switch my plan around a little bit and do some trigonometry instead starting today. So with basic trigonometry, this is a concept in grade 10, so I do want to review some of these concepts before we jump into anything new. And the first thing we're going to review is Pythagorean Theorem. Now before we get to that, please make sure that for now your scientific calculators are in degree mode, and there should be some sort of setting on most calculators that allow you to switch to degree mode. And to know if you're in that mode or not, there's usually either a DEG in the window of the calculator or a D in the window of the calculator somewhere. Some of your cell phones do not have the ability to go into degree mode. They use radian mode, which we may be looking at a little later on. But we're using degrees for now. So if you don't have your calculator in degrees, you won't get the same answers as me. So I'm just letting you know that ahead of time. So Pythagorean Theorem. So this is all stuff that you're supposed to know. So we're going to go through it, I hope, relatively quickly. And I'm going to actually start with the only example that I'm worried about when it comes to students making mistakes. And I'm going to label this first triangle here. I'm going to put a 16 here, and I'm going to put a, let's say this side is 5. Now, I'm making these numbers up. I'm not saying that these answers are going to be to scale, okay? So don't worry about the scaling of the pictures. You usually shouldn't be looking at the scale of the pictures anyway, because they're often drawn not to scale just to try to throw you off. So it's an idea here. The idea here is to trust the mathematics to check to see whether the picture is to scale or not. So what is the Pythagorean Theorem? The Pythagorean Theorem is a formula that basically tells us how three sides of a right-angled triangle are related to each other. There are some very interesting proofs of the Pythagorean Theorem out there. There's one particular one on YouTube that deals with water inside of containers. But basically what the Pythagorean Theorem states, if you've never seen this before, it's worth talking about even just as a review. Yes, and this is going to be my ugly right angle triangle here. If you take a square and draw it along this side of a right angle triangle, and you take another square and draw it along this side of a right angle triangle, and you take another square and do the same thing on the third side, those are all supposed to be squares. What you'll discover is if you cut this square up and you cut this square up, that the area of both of these squares, the red and the blue one, will equal to the area of the third square. All the time. And that works for every right angle triangle. Okay? So the video that I'm talking about on YouTube, they fill the red square and the blue square up with water, and they spin it on a wheel, and both of those completely empty out into the third square. Okay, so it's going to happen every time, no matter what right angle triangle you're dealing with. If the area of two squares sum up to the area of a third square, well, how do we write the area of a square? It's side squared, right? So if we call this side A and we call this side B, now the hypotenuse side has to be side C for this formula to work, okay? So it's A squared plus B squared equals C squared. I'm sure I'm not surprising you at all with that formula. But what I am concerned with is if the triangle had not been labeled A, B, and C, like I labeled it for you, but if it had not been labeled A, B, C, I'm going to show you the most common mistake I see in students doing Pythagorean Theorem. and that is this. Okay, that is the most common mistake I see with Pythagorean theorem. And the reason is because the students aren't stopping to remember that the c has to be the hypotenuse. Now, I've got to tell you, when I learned this formula in high school, we actually called this h squared to make sure we knew it was the hypotenuse. But you run into problems by calling it h because h is often used for the height of objects, and oftentimes in triangles you're actually working with heights of objects. So there's a little bit of a problem with using h. So it is required that you remember that that c has to be your hypotenuse, which means that that is wrong. Okay, you cannot just always substitute the numbers that you're given into a and b. You have to know where they're going. And like normally I would actually isolate the variable before I would substitute my numbers in, but I just wanted you to see exactly what I'm talking about here. This is the correct way of substituting into that formula. I want to make sure my b doesn't look like a 6 there. Okay, the c is the 16. So that means that you have to do a little bit of algebra to get the b squared all by itself. And we're going to be subtracting 5 squared. Now, I've actually seen some teachers teach the Pythagorean theorem as two separate equations, one equation for when the hypotenuse is given and one equation for when the hypotenuse is not given. I do not like to do that. You should be able to remember that the hypotenuse has to be the c squared, okay? And now we have to follow BEDMAS. So another mistake I have seen in the past, be very careful, I have seen people tell me that the answer is 11 squared here. You can't do that. You have to do the powers first. And at this point, I would have to refer to a calculator. So I'm just going to do this off screen. I'm not going to pull the calculator on screen just so that we can save some time. So we have 16 squared minus 5 squared. And that is equal to 231. And then we have one more step to do. We have to get the b all by itself, which means we have to destroy the square, which means we're going to use a square root, which is the anti-function or the inverse function of a square. So we're square rooting 231. And because we're looking for a length here, we don't have to consider the plus or minus answer to that. So square rooting 231. And I'm getting, if I didn't make any mistakes, approximately 15.19, so I'm going to round it off to 15.2. Hopefully I didn't make any mistakes there. Okay, so I would consider this, like I said, the most difficult, and it's not difficult, but the most difficult Pythagorean equation question, simply because of having to remember that the 16 has to be put into the c squared. Now, the easiest type of Pythagorean equation, and I'm just going to drop the units for now, folks. If this was centimeters, our answer would be centimeters, okay? This is the easiest one because we are looking for c. C is actually our unknown, okay? So you could even write this equation backwards. I'm not sure which way is forwards and backwards, but I mean with the c already on the left-hand side of the equal sign so that we're ready to isolate it, okay? And I've seen some people even do this right away because we are going to have to square root that answer. And I'm just showing you some techniques here to make your work a little bit faster, okay? Good calculators, you can actually type all of that in one step. But like I said, I'm just going to do this calculation off to the side here. So we've got 8 squared plus 12 squared, which is giving 208. And if I do the square root of that, I'm getting 14.4 as my final answer for the hypotenuse there. And these questions kind of self-check, right? We know that the hypotenuse is special in a right angle triangle because it's supposed to be the longest side of the triangle. It's also across from the 90-degree angle. So there's a couple of ways of finding the hypotenuse, longest side or across from the 90-degree angle. So if I had gotten a number here that was smaller than 12 or 8, I would know that I had made a mistake. A lot of times in this scenario, if students don't do things right, they'll sometimes get a negative as an answer to these subtraction here. And you can't square root a negative number, so there's a mistake there too. So it kind of self-checks to make sure you're doing it right. And these are concepts that aren't that difficult anyway, but I did want to review them with you, just to make sure we're starting all on the same page. Any questions about the Pythagorean theorem? Because I'm not planning on spending much more time than that on it. Okay. If there are any questions, let me know. I don't see anything popping up in chat. Let's move on to Sohcahtoa. Now, Sohcahtoa, I'm hoping you've heard that acronym before. It's just a way of remembering which ratio do you use based on the two sides that are given to you. There's the sine ratio, the cosine ratio, and the tangent ratio. Now, I want to make sure you understand what that word means. What do I mean when I say ratio? So in other words, what does sine 30 give us? When I do sine 30 on a calculator, or cosine 45 on a calculator, or tan 57.3 on a calculator, I'm getting these weird decimal answers most of the time. Sometimes they're nice decimals. What is that decimal? What is sine 30? What does it mean? And I'm hoping that you actually did this little activity in grade 10 or at some point in your math high school careers. But it's based on the idea of a very interesting property of similar triangles. So what do I mean by similar triangles? Does anybody remember what is special about these three triangles if I tell you that they're similar? There's actually multiple things that are special about them. Can somebody tell me at least one thing that's special about them? Okay, good. Not only do they all have one angle in common, not only do they have two angles in common, they actually, all three of them, have all three angles in common. And that's pretty easy to prove. And there's some of the other ones, so I'll get to that in a second. If I tell you that the corner angle here is 90 degrees, and I tell you that this angle here is 30, we know that all three angles in a triangle have to add up to 180. So knowing two angles in the triangle immediately tells us that the third angle has to be the same if it shares those two previous angles with another triangle. Okay? The other thing, and one of the most important things about similar triangles, is that they're proportional. And I previously did this on my calculator, especially for this last one here, to make sure this works. But if you look at the two sides that I gave you here, the 1 and the 2, look at the two sides given here. Proportionally, they're not the same, they're similar. What did I do to 1 and 2 to get 4 and 8? If you multiply 1 by 4, you get 4. If you multiply 2 by 4, you get 8. That's proportionality. You can also do proportionality in another way. You can do 8 divided by 2 gives you 4, and 4 divided by 1 also gives you 4. You can also do 2 divided by 1 gives you 2, 8 divided by 4 also gives you 2, and that particular proportionality helps us to see this one is 17.4 divided by 8.7 also going to give you 2, and it does. So these three triangles are proportional to each other. They also all have a 30-degree angle. Now, the 90-degree angle is just there to tell us it's a right-angled triangle. So very, very rarely do we ever talk about the 90-degree angle because it's not the special angle. The special angle here, the one that defines the triangle, is the 30-degree angle. And I actually took out a protractor to prove, and I tried to get it close. It's not easy on the smartboard here, but if you look at this angle here where it starts at 0, it's pretty much at 30. Okay, so I tried to make sure that all three of these triangles were exactly proportional. It's a little hard to see on the small one. All right. Now, what does that do? Well, here's what the mathematicians discovered. If I take the 1 and divide it by 2, and I take the 4 and divide it by 8, and I take the 8.7 and divide it by 17.4, what answer do I always get? I always get 0.5. And that's true for every 30-degree angle right angle triangle. Not just these three. That is a pattern that exists for every one of them. So when mathematicians see a pattern like that, a pattern that gives you a constant answer, they often will try to make some sort of mathematical relationship equal to that constant answer. And because mathematics is fairly old, the language that supposedly this came from was Arabic, but then was translated into Latin when Latin became the language of education in the humanities history. And they talked about the word sine. Now it is S-I-N-E, but we often will truncate that just to S-I-N, okay? What does that word mean? Well, it means the ratio when we divide the 1 by the 2, when we divide the 4 by the 8, and when we divide the 8.7 by the 17.4. For every triangle, if you're doing the division of the side that's across from the angle by the side that's the longest side, you're always going to get a constant number. So they just called it the sine of something. Now, what did they call it the sine of? Well, what did I say defines these triangles? The angle 30 degrees defines these triangles. And I hope you understand that we usually use the letter theta. I'm hoping this isn't the first time you see that letter. It's a Greek letter. We usually use Greek letters to represent angles. And sine theta would be equal to those two sides. Now, they actually named the sides so that we knew, as mathematicians following in their footsteps, what sides are they talking about? Well, if I'm going across the triangle from the angle to get to the first side in my ratio, we call that the opposite side, because it's across the triangle on the opposite side of the triangle. And we've already talked about the longest side being the hypotenuse. And that's what they decided to call that ratio. The ratio of the opposite divided by the hypotenuse is equal to the sine of the angle. And no matter what triangle that is right angled that you're working with, depending on what theta is, you will always get the same ratio when you divide the opposite by the hypotenuse. And that's a powerful thing. If you think about it, if I told you that when you divide two sides, you always get 0.5 as an answer, okay? If I don't tell you one of the two sides, can you tell me it now, looking at that equation? Everybody should be able to tell me what x is. What x value divided by 12 gives you 0.5? And I'll wait for the answer. Exactly. It's 6. 6 divided by 12 is half of the difference to 12, right? 6. So that ratio is all, if we know this decimal and we don't know one of the two ratio numbers, we can calculate that ratio number. Okay? We can calculate the x. And that's exactly what sine, cosine, tan are. They're just those missing ratios of every possibility of the division of two sides in a right angle triangle. So cosine theta is which two sides? Well, this is where Sohcahtoa comes in. Sohcahtoa is just there to help us remember which two sides are connected to which cosine, sine, or tangent ratio. Okay? So cosine is so this comes from so. This comes from ka, So the cosine is equal to which two sides? Well, what does A stand for? And you've seen this before, I'm sure. A stands for the adjacent side, and H also stands for hypotenuse again. And then tan theta. Tan theta is equal to what two sides are we dealing with? Well, TOA will help you remember. It's the opposite side divided by the adjacent side. And we need Sohcahtoa when we're dealing with a question in a right angle triangle that doesn't have all three sides involved, where it has one side and an angle involved and we're looking for another side. So I'm not sure if you've ever had that discussion before as to where sine, cos, and tan come from, the fact that they're related to 3 or more or a billion similar triangles. But even if you did, I think it's important to review it, because I get a lot of students that'll wonder, what is sine theta? What does that mean? Well, it's just the constant number you get when you divide any opposite side by any hypotenuse side in a specific triangle that has a specific angle in it. And now we can actually start to use that knowledge to solve some problems. So let's say, and I'm going to try to draw right angle triangles as nicely as possible here, folks, but again, it's really difficult to do on my tablet. That's about as good as it's going to get. I don't want to keep calling down these tools for straight lines, because it's going to take forever to draw these things. So we're just going to pretend that that's a nice right angle triangle. Let's say that I told you that this angle here, and I never draw my angles perfectly to scale, folks, so we're going to trust the numbers that I give you here, okay? Let's say that angle was 20 degrees. And let's say I told you that this side here was, I don't know, 18 meters long, and I asked you to calculate that length there. So the most important thing about right angle trig is, can you identify which two sides you're working with? Now, you should never identify all three, okay? This side is not participating, so we don't need that side. We just need to know what are the two sides that are participating in this particular question. Are they opposite, adjacent, or hypotenuse? So the word adjacent means next to the angle. Now, there are two sides that are next to the angle. That side and that side form the angle. So either x is the adjacent or 18 is the adjacent. Well, 18 can't be the adjacent, because 18 is already defined by the longest side of the triangle as being the hypotenuse. So I know that 18 is the hypotenuse. That means that x has to be the adjacent. It's the only other side that's touching that angle. And now that I know that A and H are the two acronym letters in adjacent and hypotenuse that we're dealing with, I'm going to think of Sohcahtoa, and I'm going to find the A and H in Sohcahtoa. And that's going to tell me that I am using the cosine ratio. So how we write this is cosine of 20 degrees is equal to the adjacent side, which is x, divided by the hypotenuse side, which is 18. Now, I've got to tell you, folks, it is amazing how a small thing can cause students so much trouble. I actually don't write Sohcahtoa the way that is normally written. When I write Sohcahtoa, I usually write it like this is the example for ka here. I usually write it like this, because for students that struggle, I don't know if there's anybody who struggles that much in this class, but for students who struggle in math, like let's say you ever had to tutor somebody. If you write the equation like this, somebody who struggles in math is going to say, hey, these are all multiplying. Okay? So you've got to be a little bit careful when you give acronyms and tricks to help people remember. So I usually write Sohcahtoa this way, simply because I've seen too often students trying to trust the equation, and when it's written this way, they think there's a multiplication involved. Okay? So hopefully there's nobody that's going to be struggling with that idea in this class, but you never know. So I may use this way of writing it down, and hopefully that doesn't bother anybody. All right, we're not done yet. We still need to isolate the variable. Okay, so let's talk about the algebra involved here. pretty easy stuff. We've got a division by 18. We've got to get x all by itself. That 18 is going to move over here. Now, normally we isolate on the left-hand side of an equal sign. This is how you should write it, by the way. Okay, now, yes, you can just type it into your calculator and find the answer. But I strongly caution you against writing it this way. Okay, because if you write it this way, certain calculators open a bracket right after the cosine symbol. It depends what kind of calculator you have. If you don't close that bracket right here, your calculator might actually find the cosine of 20 times 18, and that's not what we want. Okay, so it is much, much better to write it with the 18 in front of the cosine 20. And then you just type that into your calculator. So now I'm actually going to switch to my calculator just to show you how I'm typing this in. Let me delete all of this stuff here, and I'll clear this out as well. So if I have to do 18 cos 20, now this is my computer calculator. It is not actually a great calculator. First thing I want to point out, see the DEG right here? If I click on that, it goes to RAD, which stands for radians. And if I click on it again, it goes to GRAD, which stands for gradients, which I've actually never ever used in all of my math in university or high school. But I have used degrees and rads, okay? So if you're one of those students that carries their calculator in their backpack or in their pencil case, and your calculator happens to get that button pressed by accident, you may not be in degree mode anymore, which is going to cause you some big, big problems, okay? So make sure your calculator is in degrees. 18 times. Now on this calculator, I have to put the 20 in first, then I have to go to trig and press cosine, okay? Now I'm still not done, because this point, actually I'm not sure, maybe I'm wrong. I'm going to press equals just to see. Yeah, I think I have to press equals to find the final answer, because this 0.939, all that is the cosine 20. So your calculator immediately does cosine 20 just to find out what that ratio is, okay? And now when I press equals, it'll actually multiply it to the 18. So it can be a little bit complex, so be a little bit careful when you're doing these calculations, okay? And if you have a calculator handy, give it a shot. See if you're getting the same answer as me right now. So 16.9. If I round it off, is what I'm getting. Now technically, if we're doing, preparing you for science as well, if I talk about significant digits right now, both of my numbers have 2 significant digits, okay? So my final answer should only have 2 significant digits, which means I actually should be rounding this off to 17. Okay? So that's, and I could show you an example of a sine scenario. I could show you an example of a tan scenario. I am not going to do that, because this is supposed to be a review of grade 10. Your homework questions that I'm going to assign to you will be the things that'll test you to see if you understand what's going on. That being said, is anything here requiring extra explanations? I'll give you a few seconds to answer. So I'm not seeing any questions pop up, so let's continue. And this is not going to be a very long lesson today, folks. I just want to go through this one last example. It may actually be the last one. What happens? What happens in a case like this? So in this case, I'm not giving you the angle. Now, I'm about to go down a bit of a insanity-fueled rabbit hole with you, just because I really want you to have a greater understanding of how this particular example works than just plugging it into a formula. And I've seen too many silly mistakes with this one to just want to fly through it. So I may talk about some weird things here. I believe I actually did discuss it briefly with you at the beginning of the year when we were talking about inverse functions. And this is where my angel and demons story comes into play. So bear with me. Okay, what two sides are given to us based on our angle? So if I go across the triangle, that is my opposite side. I have two sides touching the angle. The hypotenuse is not participating, so this has to be the adjacent side. So we're talking about adjacent and opposite and adjacent. That comes from TOA. So that tells me what I'm doing to write out the formula. Now this time we don't know the angle, so we're just going to write tan theta is equal to opposite over adjacent following the formula. Okay? Now, I have seen students do this. Never, ever do that. Okay? Now, what is a student doing if they do this? And this silly thing is that'll actually give you an answer on your calculator. It won't be the right answer, but it'll actually give you an answer on your calculator. The student who does that mistake is thinking that this is a multiplication between tan and theta. Tan looks like a bunch of variables, and theta is another variable. When you have a bunch of variables next to a variable, it usually is a multiplication. But tangent is not a variable, okay? And just to make my point clear, if I gave you x squared is equal to 5, is this how you would isolate x? By moving the square and dividing it over to the other side? No, obviously not. You have to consider this as being a function. Tangent is a function. Okay? What anti-function kills tan? And I'll let chat answer that for me. Correct. Now, inverse tangent actually has a name. Does anybody know its name? I'm not seeing the name pop up, so I'm assuming you maybe don't know what I'm talking about. Yes, there it is. It is the arctangent. Okay? The symbol for the arctangent on your calculator is tan minus 1. Okay? Now, I'm sighing because this is where my life as a teacher I start questioning my life choices. Because of all of the problems that math teachers in the past have caused me by using symbols that are dumb because they're used other places that's going to mess up students. Okay? So I apologize in advance for this rage-fueled discussion that we're about to have. This is not a power. This is not tan to the power of negative 1. Nor is it a negative tangent. And we've done the exponents section now, okay, which even makes this worse, because I have had students think that tan negative 1 means 1 over tan. It is not. Okay? So, I have actually seen some textbooks write this, and I may have talked to you about this before, as tan inverse. Okay? And this comes from, by the way, this comes from our f negative 1 function notation of an inverse function, right? And I believe I had a bit of a rage field discussion with you about that at that point, that symbol is one of the worst symbols I've ever seen used to represent the inverse function. So, and all I can say is don't be that person. Okay? Make sure you understand that in the context of this question, tan negative 1 is not a power. Tan negative 1 means the inverse function of tangent. So how does an inverse function behave? Well, when you put an inverse function in front of a function, what does it do? And whatever we do on one side of the equal sign, we also do on the other side of the equal sign. Okay? So here's how I, in my mind, have these little things that make mathematics a little bit more interesting to me, and I think I've done this before, and I'm going to do it again. Okay? I consider tangent to be some sort of evil demon. Here are the horns. Okay? That has swallowed theta. And the only thing that's going to kill a demon is an archangel. And that's, in my mind, that's why this is called arctan. Okay? So here is the archangel. Arctan. And this is Arctan's sword. And Arctan is going to kill the demon, but unfortunately when an archangel and a demon fight, they usually both die. And that means that the only thing that's left on that side is theta. And that's what you type into your calculator. And no, I'm not expecting you to draw archangels and demons. Okay? But it's fun to share the insanity of my mind sometimes with students, because it, and as funny as it sounds, that I'm hoping it's funny, this kind of thing actually helped me get through university. Making up these stupid little stories to help me remember how things work, and as a teacher, then, you know, promoting these. And this is not the end of the story. When we get into trig identities later on, this whole story is going to come back. So I kind of need it because this is foreshadowing. Okay? Anyhow. So how do you type that into your calculators? And it really depends on the calculators you have. So let me switch over to mine here. On this particular calculator, I'm going to delete all this so it's not in the way. On this particular calculator, what I need to do is I need to do 5 divided by 8 equals first. Then I have to do second tan. And now I don't press the equals after it. That is the answer. Okay? So 32 approximately degrees, and that's good enough. So my final answer here is 32 degrees. And now not only do we have a way of finding unknown side lengths if we're given an angle and a side in a right angle triangle, we also have a way of finding unknown angles if we're given 2 side lengths in a right angle triangle. And that's going to be the end of the lesson for today. So I have summarized and reviewed with you how Pythagorean theorem works. I have looked at Sohcahtoa for finding sides, and I've looked at Sohcahtoa for finding angles. I did not show an example of every kind. I am expecting you to know how to do those, and I will be giving you some homework today to prove to yourselves that you do know how it works. Some of the homework questions may be a little bit more challenging. I don't think there's anything that you can't get done, though. But as always, if you have any questions, you can email me and we can discuss them. So I am going to say goodbye for the recording.